I'm going to go ahead and start. Welcome, everyone. This is a series of seminars that we're doing that's sponsored between the GRSS and the Metro LA chapter. I'm Rashmi Shah, and I'm the chair of Metro LA chapter. And what we have done is we requested our members for presentations, and we got a bunch of them. So there's a series, and this is the second one in the series that we have ongoing. So without further ado, I'm going to introduce today's speaker and let him speak. Today's speaker is Dr. Hesham El-Askary. He's a professor of remote sensing and Earth System Sciences in the School of Earth and Environmental Sciences, and holds another appointment at the School of Computational Sciences at the Smith College of Science and Technology at Chapman University. Professor is also a member in the Center of Excellence in Earth Systems Modeling and Observations. He serves as a professor of environmental sciences and is currently on leave with the Department of Environmental Science Faculty of Science, Alexandria University in Egypt. He has served as an academic advisor for the Department of Environmental Sciences, Alexandria University between 2000 and 2008, and was also elected by the faculty administration to serve as the member of Quality Assurance Unit responsible for applying the Ministry of Higher Education strategies as a component in the accreditation process. He has published over 100 refereed research publications, conference full papers, and book chapters, and has research supported by NSF, NASA, USDA, and EU. He received the Saudi Arabia Award hosted by the Arab Administration Development Organization, affiliated with the League of Arab States, for the best published article in environmental management among 150 articles in 2006. And he's a member of IEEE, AGU, EGU, COSPAR, and Phi Beta Delta Honor Society. So we are really honored to have him as one of the speakers today. And the topic that he will be speaking on is Earth observation solutions addressing SDGs in support of key environmental challenges. With that, please take it away. Thank you.
Thank you so much, Rashmi, for the kind introduction. And it's quite an honor and pleasure to be here with all of you today. Can you hear me fine?
Yes, we can.
Awesome. So I'm very happy to be here with you guys today, and would like to extend my appreciation for the IEEE GRS Metro LA chapter for the kind invitation. As Rashmi mentioned in the title of my presentation, I'm going to be talking about Earth observations, the usage of Earth observations to address key environmental challenges along the Sustainable Development Goals. Today, I would like to focus on showing some innovative work in the extensive usage and the utilization of satellite Earth observations. And I'm going to be highlighting specific SDGs dealing with biodiversity and climate action. We are aware that the Earth system science is quite complex, and all to these complexities embedded in the field of Earth system science. My research group employs AI and machine learning breakthroughs to combine with Earth systems knowledge in order to address issues that are related to different kind of environmental challenges. Let me start here by talking a little bit about the primary global risk report that was shared in 2019, the 14th edition through the World Economic Forum. And in this report, in this meeting, they were highlighting the most important challenges, or I would say risks, which are facing humanity. They range from weapons of mass destruction to financial crisis and much more. But if you take a look here, you will see in this chart, the vertical axis is talking about the impact of those kind of risks, and the horizontal is the likelihood of their occurrence. And you can see that environmental risks, which are in green color, they are all in quadrant 1, which is indicating the highest impact and the highest likelihoods. Among those, like failure of climate change mitigation, adaptation, extreme weather events, natural disasters, all of these are among the highest impact and the highest likelihoods. Loss of biodiversity, you can see here, even water crisis, although it's of environmental nature, but it's like, it's highlighted under the societal kind of risk, and you can see a lot of other things. But like the point I'm trying to make here is the highest likelihood, the highest impact of environmental related risks. The historical trend of the World Economic Report shows that the prominence of the environmental risk continues to rise. You can see in this two charts, the top one is based on the terms of impact, the bottom based on the terms of the likelihood over the years, and you can see the colors are changing over time, and they are getting more towards the green color, which are of environmental nature. And as I mentioned, they are mainly around the extreme weather events, failure of climate change mitigation, adaptation, and natural disasters. And these are key risks which are facing us right now. And like, we're not talking about something that we're not observing ourselves, but we are already observing the massive increase in the magnitude and the frequency of natural disasters happening around us in terms of loss of biodiversity and as such. A few years back, like, the United Nations, like, issued different kind of initiatives. You can see these are 3 global agendas and policies where Earth observation have been a tool and, like, a key in addressing those global agendas, namely climate action, the Paris Accord Agreement, the Sustainable Development Goals, and the disaster risk reduction, the Sunday framework. We are trying to show how Earth observations can be used in order to address these global 3 agendas and policies, and how it can be used in order to help decision makers, stakeholders to take better action. As you can see here, I'm going to be showing some work which is supporting those 3 global agendas. But I'm going to be focusing more on the SDGs components because of the inherent nature of challenges which are embedded in those in the way we are achieving those SDGs. And there are 4 major challenges when you talk about different kinds of nations: missing data and the evolution of the SDG indicators. And this is happening across the globe. Like, there are a lot of nations which are suffering from lack of data and like, the incompatibility of data with other domains and other locations, and that poses a problem, and it's quite a challenge. The complementary, non-complementary interconnections between different SDGs, complicated and varied problems in quantifying and monitoring indicators, because different nations will have different capabilities and different abilities to report on those SDGs. So it is not an easy task for everybody. And like, our expectations are going to be different based on the location, and that can be a challenge, and also some difficulties in modeling indicators. And for that, we can see in this triangle that we have a hierarchy of indicators, like, falling between different tiers: tier 1, tier 2, tier 3. And as you can see, we are talking about 17 SDGs with 169 targets, with 232 global indicators in order to follow up and review their progress. Those different indicators are falling in different kind of tiers, like, where tier 3, which are like, the highest level of these indicators, which can really be beneficial in the way we are reporting. But unfortunately, not everybody is able to report on those indicators. And today we are going to try to show how Earth observations can be quite impressive in addressing some of the higher tiers SDGs, or higher tiers, indicators addressing specific SDGs. And this is also another source of information, EOS, for SDGs coming from the United Nations, and also, like, talking about how Earth observations can be used in order to transform the world, and, like, to be used for monitoring the goals, the targets, and the indicators, to track our progress in achieving those indicators and address key environmental challenges. From this table here on the right hand side, you can see some of the targets that we would like to address under specific goals. So these are the goals, the 17 goals that I mentioned, and in these goals you can see specific targets which are which can be of Earth observations nature, or Earth observations can play a role in them, and you can see the different levels. And also here some of the very specific indicators that we are trying to address. So in our work, we are always trying to go back and see the relationship between what we are observing, what we are doing using Earth observations, and how they can address specific challenges, or how they can address specific targets or indicators for those SDGs. In today's presentation, I'm going to be focusing on specific SDGs, namely SDG 6, addressing clean water and sanitation, where Earth observation data is key for water resources monitoring. And you can see here, I'm highlighting some indicators which can be assessed using Earth observations. SDG 11, namely sustainable cities and communities, also where Earth observations can be a key for monitoring urbanization process. I'm not going to be talking a lot about, I had some work that I wanted to share about slums and things of that sort, but I don't think I'm going to have enough time to cover all the material I have today. So I'm going to highlight a little bit about air quality, PM 2.5 and PM 10 in specific cities, specific locations. Other SDGs that I'm going to be talking about today as well, SDG 14, life below water. Namely, I'm going to be talking about coral reef habitats across the globe in different locations, ranging from the Pacific all the way to the Red Sea. And Earth observations is key for monitoring the health of oceans. So we talk about chlorophyll content, coastal eutrophication, and others, but today I'm going to focus more on corals. And also life on land, where Earth observations can be used for monitoring the changes of land. I'm going to be talking a little bit about desertification and lack of water resources in some localities, as well as mangrove habitats and the expansion or the extension of some of these habitats in different locations. So these are some of the SDGs that I'm going to also be touching bases on today. Life on land, as I mentioned, and life below water. And if time permits me, I'm going to shed the light on a project that we did that was supported by the Horizon 2020 framework under the EU for affordable and clean energy, where we developed a solar atlas, the first dynamical solar atlas for Egypt, and currently is being used by the government as the main source of information for solar-based projects. The first case that I'm going to be talking about today is changing trend of the water variables and the groundwater recharge pattern in the Nile Basin countries. We are aware of some of the issues happening now in Africa because of water resources issues, as well as transboundary. When we talk about the hydrological cycle, or as you can see from this diagram, closing the terrestrial water budget using remote sensing observations, you can see that we always try to find the balance, the energy balance and the water balance. And you can see from this chart different kind of variables and parameters which are showing the atmospheric water balance, the energy balance, the water balance. And some of these parameters, we are showing how Earth observations can be used in order to address them, ranging from radiation or surface temperature, the atmospheric variability, clouds, water vapor, and as such, coming to some of these very important variables and parameters for the hydrological cycle and for the water balance, and talk about the water budget in general, namely soil moisture, precipitation, evapotranspiration, runoff, and the underground water. So you can see from these equations, we are trying to calculate the water balance, precipitation, evaporation, transpiration, runoff here in such equations, and how we can use Earth observations in order to fill some of these gaps or to talk about some of these variables. These are some of the hydrological variables which have been addressed over the course of time by different kinds of satellite missions, and how they have been monitored and assessed. And this is what we are trying to do in some of our work and analysis, the usage of Earth observations to address some of these hydrological variables, namely TRIM satellite, where we are calculating or measuring precipitation variability. And this is just a composite climatology for the month of December over the course of few years. You can see here, the regional distribution of precipitation anomaly obtained from TRIM. Similar stuff here, we are focusing more on the Nile Basin watershed, going all the way from Egypt in the north, passing by Sudan and Ethiopia, which is the upstream country. And there is a lot of issues right now between these three nations because of the Jerd Dam. And like, this kind of work is quite important because it shows, like, some of the indicators deal with transboundary water and water sharing and operations. So earth observations can be useful for decision makers in terms of management, in terms of operation. This is another product, El-Askary, which is showing the evapotranspiration, and I'm just showing the climatology here, just like, for 1 month, for the sake of timing, just to give you a flavor of earth observations and what they can do and how they can measure. This is what they can measure. This is the LDAS products, showing you the soil moisture over the same location, and here the NDVI, normalized difference vegetation index, which is a measure of healthiness for vegetation in the 3 different countries along the Nile Basin. And here the last one, showing the terrestrial water storage, the underground water anomaly obtained from GRACE gravitational mission or experiment. This is one of the most recent map, which was issued by NASA, talking about the drought in the Eastern Mediterranean, which is the worst of the past 900 years. And this is showing you the anomaly coming from GRACE, which is the Gravity Recovery and Climate Experiment. So basically, it is not here measuring electromagnetic spectrum, just like the gravitational anomaly. I'm pretty sure, like, the audience might have the background necessary to be aware of what I'm talking about. But like, the long story short, here we are observing like, the extent of this kind of drought anomalies, like, the lack of water resource or the underground water anomaly. You can see here over Egypt, like, very, very low water storage, which is a very dry spill, and also, like, the southern basin of Europe here, the Mediterranean basin, like you can see here in Europe, also in the Gulf region and the MENA region. So it's quite dry in this region. That's why we have been trying to focus on that watershed and collecting a lot of different data sets addressing like, different compartments or different components of the hydrological cycle in order to see the impact of long-term droughts or even, like, these kind of projects, which is built in Ethiopia. And here the different watersheds that we are looking at in order to assess some of these data sets or some of these products and those parameters ranging from evapotranspiration, soil moisture runoff, underground water, NDVI, water index, and as such. So a wide range of earth observations, wide range of parameters and variables that we are using in order to address water issues in this part of the world. This is a map showing you the negative changes of the water equivalent height, which corresponds to the mass concentration, showing you, like, the drier it is in Egypt over the course of time. These what we call mass counts. So each, like, every single square of this represent that location, and you can see those red colors represent how dry it is, and you can see the decline in this water equivalent. And as you move down in Sudan and Ethiopia, it gets a little bit better, but over here, which is the downstream country for the River Nile, it's really like, lacking a lot of these water resources. So for that, we started collecting more and more observations, and as you can see here, we are trying to look into the water budget by calculating like, different kind of variables and a different lag. So we wanted to see like, the time domain and the variability over time, how it can affect the different components of the water budget, precipitation, evapotranspiration, and as such. And you can see at lag 0, you don't see much impact or negative impact here. You see, like, there is a negative correlation here, but over here it gets more and more positive, which implies that over the course of time, like, until like, infiltration happens and the precipitation, it takes a little bit of time. So that's reflected by this kind of lag, and that's why the recharge pattern is changing, as you can see over these watersheds. Work like this would be addressing specific indicators, as I mentioned, like, which can range from different tiers, like, from tier 1, where we can talk about level of water stress, all the way to change in water use efficiency over time. And this is the idea here. We try to show how earth observations can be used in order to address specific indicators which are of higher tiers because they are going to bring us more valuable information. This is some of these variables, some of these parameters, as you can see here, for the different nations. This is the entire Nile watershed, and this for different nations here in Egypt, Sudan, and Tanzania, for Uganda, for Kenya, and for Ethiopia. And what we are showing here, these two curves, the blue one represents the underground water supply, and the red one is the difference between the precipitation, evapotranspiration, and the runoff. So you can see here, like, the intake, for instance, in the case of Egypt, is like quite normalized, so you don't see much variability, but you can see the decline here in the underground component. So that kind of declining trend, which is opposing to some other increasing trends in other nations. And here we are showing the lags, as I mentioned, between those three variables and the water equivalent, which is measured by GRACE. And this is important because we have global issues with water across the globe. There is a lot of water stress, and you can see here, this is some of the GRACE anomaly. All these red spots reflect lack of water resources. And now we're going to focus a little bit on Saudi Arabia, on the Gulf region, and you can see here that decline in the terrestrial water storage anomaly over Saudi Arabia over the course of time, reflecting these kind of dry regions. And this is what we are trying to show for decision makers and stakeholders, so that they can start thinking about other options and to be more innovative about water resources, or addressing some of these problems that we are facing at a global level. Moving on, this is a similar work that we did here over California, where we were looking into the El Nino impact. We are aware that El Nino season, when it happens on the West Coast in California, it brings a lot of rain. That was very famous in the 1997-98 El Nino event, which took place on the West Coast, and we observed massive amount of rain and precipitation. And that was different from what we observed about, during 2015, 2016, where we were promised to have a massive amount of precipitation on the West Coast, owed to the so-called Godzilla El Nino that was mentioned back then. However, our work using a variable which is called the PZI, or the Palmer-Z index, showed something totally different. Before the season hit us and before the El Nino took place, we were doing some kind of learning on this PZI data. So I'm showing you here two graphs. The gray scale, the gray plot represents the observed PZI. We had more than 150 years of data. And I'm showing you only the validation data set. So we use the recurrent neural network algorithms in order to study or to learn from that long time series, 100 years of data we learned from. And this is just the validation data set, which is another data set that was never touched by the model to learn from. So you can see here the intercomparison between the observed PZI and our forecasted from our model. So the dark line is our model, and it shows you the level of matching between our model and the observation. So basically, this period was never used in the training data set. So we use the first 100 years of data to train our models, and then we use the following years in order to validate. And this is what we call the validation data set. And you can see here the high matching. And we did the same thing for the most recent season from 2006 until 2016 back then. And you can see here there is a very good matching of the two observations as well, the observed PZI and the forecasted PZI, until this point here, which is the end of 2015. And then the beginning of 2016, this is where we didn't have any kind of observations, because this is what we were projecting, which is showing you a decline. In other words, we were not expecting to have massive amount of rain. And with a little bit of zoom, on this red polygon here, you can see that the error bars were like, very limited at the beginning of our prediction. And of course, over time, like, as you move in months, like, you get a little bit of divergence, or your model doesn't perform the way you are expecting at the very beginning, which is fine, which is expected. So this work was submitted to the Atmospheric Research, one of the most prestigious journals, and we submitted that work back in March 2016, at the very beginning of the year. And the work, because it was quite intriguing, because we were talking about El Nino, that everybody's expecting a lot of rain, and we were totally seeing the opposite, that we observed a very strong drought projection that's going to happen in California. And the work stayed under review for almost a year. So it was received March 2016, and then we got the acceptance towards like the end of the year. So like 9 months, basically they were waiting to see like the season, and to see if it's going to be raining or not. So very, very important work that we did on this using recurrent neural networks, and that was a very good application for drought projections. Another sustainable development goal that I would like to mention here is sustainable cities and communities. And here I'm going to be talking a little bit about air pollution that we are using, or we are assessing over different countries and different locations in the MENA region, using like, sentinel data set, like, targeting specific variables, namely carbon monoxide, NO2, ozone, UV, like ultraviolet aerosol index, and different other variables which are reflecting or assessing like, the level of the water air quality in these locations. So here you can see a time series over specific like seasons and specific times over the city of Cairo, which is the capital of Egypt. And here you can see more on a regional scale maps of the tropony of different kind of variables, and the MERA2 product, the AOD distribution for the MENA region within different kind of seasons. As you can see here, different variables, different parameters, and like, we are just assessing, like, the regional extent of these variables, like a couple of variables here and another two here, NO2 and ozone, over different locations in the MENA region, using Earth observations. And we did some kind of validation as well with ground observations. Here we are showing correlation maps between daily anomalies. So here, like, the NO2 and carbon monoxide, the first one, and here a correlation between the carbon monoxide and UVAI aerosol index, and here NO2. So we are trying to see like, the correlation between different variables, and that can talk to us about the microphysics of different kind of aerosols. We use different kind of sensors like lidars and calypso profiles in order to look into the backscattering, and as such, talking about what air quality, and talking about the extent of some of these aerosols in that region. This work was published as well in the Remote Sensing Journal, talking, like you can see here, a couple of studies. One of them is more local, and the other is more regional. And here we were doing some kind of intercomparison between ground observations as well as satellite observations, using different kind of models and sensors as well, against ground observations, PM10, and different kind of variables and parameters from the aerosol robotic network. Again, like, this kind of work addresses specific indicators under this specific goal, which is targeting good health and targeting sustainable cities and communities. I'm gonna, like, shift gears here to life below water, and here I'm going to be talking a little bit about the coral reef work that we did in the Pacific Island and the Red Sea. I'm not sure if I'm going to be able to show the Red Sea work or not, but the question that we're trying to raise here: how can we measure changes in the amount of the coral cover efficiently at scale? There are a lot of different kinds of challenges when it comes to coral detection either like, you'd like to do the water column correction, the pixel and reef heterogeneity, site-specific geomorphology differs from one location to another. The fact that you have temporal data is not that easy, and the water turbidity, all of these are different kind of challenges that it comes to us when you are trying to address coral habitats, or when you are trying to study coral reefs. This is just the scientific basis, the background for the calculation of the water column and the atmospheric corrections, where you are assuming the dark pixels and you are looking into removing the impact of that water column on top of the coral habitat, so that the actual observations that you are doing or you are getting is reflective of the healthiness of these coral colonies, and to talk about different kind of bethnic environments. We started the work by looking into Hurghada, Egypt, and do intercomparison and change detection analysis over 3 decades, ranging from 1987, 2000, and 2013. That was old work that was published in 2014, but that was the basis of our most recent work that we published in 2019 and 2020. So you can see on the top image here, the satellite images for these 3 years, and on the bottom one here, where we are doing masking. So a step in, different kind of steps in the pre-processing, where you are removing the island component and the water component, so that you can focus only on the different kind of marine habitats that you have. Here we are showing some kind of supervised classification, because we were lucky to have some ground observations at specific location. So this island here, which is called Shabel Erg, we were able to collect some like field data from that location, and it was very useful in order to apply this kind of supervised classification on the entire domain, so that we can assess the different kind of changes from coral habitats to other classes and macroalgae, sand, subtidal, seagrass, sand, intertidal, and different kind of marine habitats, and all of that in order to assess the impact of urbanization, as well as any kind of environmental stresses or environmental risk posed on these environments. This is a satellite image for that region of interest in 1985, and you can see here the extent of the corals and the extent of those marine habitats in these areas. You can see here some mangroves. This is a Giftun Island. All of this part of the Red Sea and Sea in 1985 was the situation, and here is the situation in 2014. And you can see the level of the urbanization and the kind of stress happening on those different kind of coral habitats. And of course, it changed the whole dynamics in the region. And you can see here the impact on some of these water bodies and the mangroves extinction. And of course, a lot of corals here got damaged, and of course, massive stress happening on this environment. The work was acknowledged on the Earth Observatory, the NASA Earth Observatory, and we found that over these 3 decades, we suffered a loss, unfortunately, of almost 50% in the coral habitats in this region of interest. However, we wanted to be able to have a more of a generalized, robust classifier, which can be used in order to evaluate and in order to assess beyond in situ analysis, because having in situ measurements from different locations is not that easy. But in order to develop something which can be used at a global scale can be quite beneficial. So we looked at those 4 locations in the Pacific, 4 islands. As you can see here, these are the locations of those 4 islands. And we were lucky to have some ground measurements, some data for these 4 locations. And we got images which matched the time of these measurements. These were the number of the ground observations that we had from those locations, and this is the distance that we had the observations from the satellite images that we had. So we collected those 4 islands, or the data set represented in these 4 islands, in order to train our models, in order to have a classifier. And likely to do the merge between satellite observations coming mainly from Landsat as well as the ground truth data. So like, we do our analysis using satellite observations, try to validate it using these ground observations coming from different sources, from NOAA and from the National Coral Reef Monitoring Program. So all of these were done from from in situ measurements and the validation to those satellite observations, so that we can develop a model or a machine learning model to learn on these observations and the matching between satellites, so that you can use satellite observations, or you can use that kind of classifier whenever you don't have such observations. So this is the creation here of the probability for each pixel containing coral cover based on the learning. So like I'm showing you here, like the probability for each pixel, and this is the classification coming from our classifier, and you can see the learning here went very well. Since we already had some ground observations, and this is based on the satellite and the validation between both. So these 4 islands were very important for us in order to create a model which can learn from ground observations, and we try now to check the model performance or that classifier performance, and it was pretty good. You can see here the area under the curve, almost 70% accuracy, which is quite significant. This classifier promised to be a useful classifier. These are the individual classifiers for each of these 4 islands, and this is the consolidated site, so that we can apply that global or that classifier that we have from the 4 sites on other locations, and this is exactly what we did. This was the paper that got published on those 4 islands, and it was also highlighted in the Landsat science domain, what lies beneath, mapping the methodic habitats with Landsat. That was very interesting work where we developed a robust classifier, or at least we highlighted the parameters and what is needed for that kind of classifier. And then we applied that classifier on another 2 islands where we did not have any kind of observation. So we added to the other 4 islands that we had before, but we have another 2 islands where no ground observations were obtained or were found, and this is where we applied our classifier on these islands. And also the performance was really good for these 2 other islands. And here you can see the change detection analysis that we performed over the 6 locations. And based on that analysis, we observed a decline in the corals for the 6th location, like 25 to almost 43%. And you can see here the decrease in the coral cover by the percentage or by the kilometers, by the spatial coverage. So that classifier was quite useful. And currently we are in the process of applying it on the Red Sea habitat. And it's promising to be quite useful. We have some locations where we are employing some ground measurements in order to validate some of these outputs that we are getting based on our classifier. Some more work here that I would like to share also on the mangrove habitats, and we are talking here about the Saudi Arabia or part of the Gulf region. Am I doing good with time?
Yeah, you're fine. Go ahead.
Okay. So in this work for the mangroves, we are studying the change detection of the forest in the Arabian Gulf mangroves, which is very important coastal habitat, and it's the home to rich biodiversity. Yet it's under a lot of threat, which might be exacerbated with our changing climate. So it's much needed work, and we are working with different entities on that. We firstly studied 3 major mangrove data sets, as you can see here, because there was a little bit of a discrepancy in these data sets. And that discrepancy was observed in the Jubail conservation. We didn't know if these areas were actual, real mangroves based on these classifications coming from the USGS or the World Atlas of Mangroves or the mangrove forest biomass. All of these are different sources of data that we used, but we did some kind of ground validation with teams from from Aramco in order to assess, in order to validate some of these locations that were classified as mangroves, but we find them to be salt marshes. So we started by correcting some of these data sets with recent maps of these biodiversity locations. It's a very important observation since the USGS data mostly used for mangrove monitoring and the model training. So we didn't have a lot of data. So the correction of these data was very important. In this work, we used Landsat spectral signatures as our tools to evaluate the issue in hand. For that, we categorized the mangroves into into a couple of regions, like either questionable regions or agreed by all data sets. We checked their spectral signatures from 1985 till 2018, and we found that the spectral signature is very much consistent, meaning that the vegetation type did not change at all. Since now we know the questionable area is salt marsh, not mangrove, we conclude that in 2000 it is still not mangrove. Therefore, we believe that the USGS mangrove dataset had a little bit of inaccuracies in these datasets. And you can see from these two plots here, or these two columns, the different locations, or the doubted and the agreed locations between different data sets and collected from different sensors. Furthermore, we used also synergistic approaches to estimate the areas of mangroves, considering the tidal levels. The tides play an important role when it comes to mangroves, because some of these mangroves are covered by water in the high tides. We use the new submerged mangrove recognition index, which is donated as the SMI. And you can see the equation here for that index. In order to detect the submerged mangrove forest, we obtained high-resolution images for Abu Ali Island, and we use it as validation imagery while using Landsat 7 and 8 images, calculate these two indices, the NDVI and the SMRI, to estimate the entire mangrove areas. We compared Landsat 7 and Landsat 8, and we concluded that the high stand mangrove in high tides and submerged is a very good matching. You can see here some of these areas where you had submerged, and we are comparing between two different satellites. And the bottom plot here is showing you the word tides, some measurements that we are getting also in order to address the level of the tides. Here you can see the good matching between both data sets, Landsat 7 and Landsat 8. And you can see here the ability to identify the total area in high tides, in terms of by hectares, in terms of those mangrove habitats. So again, Earth observation was able to highlight areas which are under stress, or even to correct some of the data sets that were listed as mangroves, and we were able to correct some of these classifications. That work also was highlighted on the Landsat science domain, and it was really a very good example, a very good showcase on how Earth observations was able to show or to assess mangrove habitats. This is another work related to change in the coastal areas, also part of the marine habitat monitoring and protection. We were talking about different kinds of islands, as you can see here, and we were talking about the impacts of global phenomena, global events like El Nino and La Nina, and see the impact of those on the coastal variability, by the rise in water, and as such, we can look into more rains and less vegetation and warming effects of those global phenomena, also by assessing NDVI, which is a measure of healthiness or a measure of vegetation. Again, the work is addressing specific indicators which are of higher tiers, or as you can see, different tiers. The coming few slides will show our recent investigation of the coastal line changes of these islands from airborne photos and from satellite imageries from 1965 until now. We just wanted to study the beach loss, which might have a direct impact on turtle nesting. So we are looking into different ecological indicators as well, and we wanted to see what was happening to the turtles habitat in these areas. We used Landsat and Sentinel imagery to show the progress of such changes, and we used deep neural network classifier to achieve that. You can see here, the change over time, and we highlighted specific locations in order to identify the exact level of changes in a couple of islands, Jana Island and Karan Island. And you can see here the coastline changes from 72 to 2000 to 2020, using these different kind of satellite measurements from Landsat and from Sentinel. And these plots are showing you the extent of the change, at every single spot here, location 1, 2, 3, 4, 5. You can see here by location, and you can see the temporal variability in this coastal areas changes. This is the time series of the estimated areas. Again, there is a moving average, just to show you the change in those two islands over the course of time. Of course, you can see some kind of outliers, but generally we're able to highlight those changes using using 3 satellites for these 2 different islands. And here we also looked at the slope of these islands. The whole idea of this work was to look into the favorable conditions for the sea turtle nesting work, which was just published in the ecological indicators for 2020. My last few slides here, I'm going to spend maybe a couple of more minutes on that, related to Earth observations and usage for addressing clean energy. So based on some satellite observations and using some machine learning and data mining models as well, we were able to develop the first dynamical solar atlas for Egypt, which has been quite useful for the country. The whole idea behind the work was looking into the amount of solar radiation, the incoming solar radiation, and how much scattering is happening to that to the incoming radiation based on dusty events. So we wanted to include the cloud and the aerosol effects in our approach so that we can have better assessment of how much scattering and how much attenuation happens. So basically, when you are conducting any kind of clean energy investment, solar energy projects, part of the problem is the feasibility study and your ability to assess how much kilowatt can be developed, can be produced from a specific location, and that can be problematic if you don't have actual correct and accurate measurements for the irradiance. So you can see here, based on our work, we were able to identify exactly how much attenuation can be happening over different regions of the spectrum, and that was very useful in order to have this kind of momentum of the pilot studies. So identifying different locations, and you are able to highlight the exact amount of irradiance, be it used for a photovoltaics project or for CSP. Egypt is not there yet in terms of concentrated solar power, but they have one of the biggest projects on this planet in Aswan in Upper Egypt, which is the Bimban location, and that's a massive solar project. I think it's the biggest on this continent in terms of photovoltaics. So we were able to identify locations like this and provide for them the actual measurements for CSP projects or for PV projects, so that you are able to see the location. And if you are an investor and you would like to expand in this area, you would have an exact measurement for the solar energy for these specific locations. If you are doing a concentrated solar power or a PV project, different locations like this were highlighted. All of that was part of the solar atlas that was funded through one of the EU projects named GeoCradle that just ended a year ago. So from all the topics that I covered today, I wanted to highlight the fact that we are able to develop products, which is addressing the 2 phases of sustainability, from research and development to operational services. How you can use Earth observations in order to address a specific idea, like you outline a business plan for it, and then you try to have some products which can be marketable, which can be of importance, which can address specific needs for stakeholders or for different locations, how you can commercialize this and expand. Some of this work that we have been working on has been used by different kinds of stakeholders. So there is a value chain in it, like, where we have the integration between academia and private sector working together in order to address the needs for different locations. So I think by that I can leave you with a couple of two concluding remarks about the importance of Earth observations addressing some of these sustainable development goals, and the interplay between Earth observations and data science is quite complicated, but we see a lot of breakthroughs and a lot of advances in these applications using cloud computing and other very powerful online resources. Thank you so much for for being here, for your attention, and I'll be happy to take any of your questions. Thank you.
Thank you. With that, I would like to open the floor for questions. If you have questions, feel free to unmute yourself and ask, or throw it in the chat and I can read it.
I think it was pretty clear. Like, it's the whole work is a trial to bring different angles of the environmental challenges and problems in different locations, and how we can help different stakeholders to address those issues. Thank you, Mr. Faiz.
Do you see the question, or should I read it?
Yeah. I see it. Yeah, it's called the PZI, the Palmer's Index.
Do you also read the question just so everyone's
sure. Sorry,
just to make sure?
The question is, what data did you use to develop the California model, the drought detection? We used something called the Palmer's Index. It's one of those drought indices that has been developed. And the good thing about the Palmer's Index that it is kind of a very long time series, and that was highly needed for training of the models. So I can share with you the article itself if you would like, so that you can read it if you are interested. It's about recurrent neural networks for California. Here, let me try to find it for you. So here's the link, and it's open source, so you can definitely download it. For the classifiers, there's another question: is any of the classifiers and the models available as open source code? Yes, most of our work we are putting on GitHub, and we are putting on the Google Earth Engine. So if you go to any of our papers, like, if you go to the Remote Sensing Journal, the publisher is MDPI, and if you just do a search by the author name, just type my last name, you're going to see some publications there, and all of these are open source, so you can just download the PDF file, and in the acknowledgement section or part of the paper, you are going to see the links where you can have access to these codes. They are open source and can be used. How GRACE data can be used for monitoring water storage? Sure. So GRACE, so regularly, like, different kinds of satellite observations are based mainly on the electromagnetic spectrum. So you are looking into the different regions of the electromagnetic spectrum, the radiations coming from the sun, and this is how you can do your measurements using optical sensors, like, in the visible, in the infrared, or even outside the optical region, in the UV or the microwave. But GRACE is mainly detecting the gravitational anomaly. So there are a couple of satellites, and based on the advance or the retreat of the underground water storage, they are starting to pull and push those different kinds of satellites, and you get the distance between them. So that reflects for you the retreat or the advance in that water. So grace has nothing to do with the electromagnetic spectrum, is not depending on the solar radiation. However, it measures the gravitational anomaly coming from the object, from the underground. Yes, Gabriella is asking, the data could be found on Google Earth Engine. Yes, it's not author name, it's the publisher, MDPI. Let me also put the link here for you. So basically, if you go to that journal, this link, this is the publisher name, MDPI, and the journal is called Remote Sensing. If you go to this link and then go in the author area, you just type last name, El-Askary, and here's my last name that you can search with. And when you do that, you are going to see some publications that are going to pop out for you, and you can use any of them. You are going to have the whole PDF file, and inside the PDF file you will see the links to the data sets that can be used. Sure, my pleasure. Question is, do we need to do some pre-processing on the data product before we apply the image analysis algorithm, such as classifier, or which kind of level the data are provided? Definitely, we need to do a lot of pre-processing. For instance, what I showed you for the coral habitats in the Hurghada region, I showed you that there was the satellite image had the island components, but when you want to classify those marine habitats, you don't want your classifier to get confused with other features which are not needed in your image. So that's why we take out the land component, we take out the water component, so that you are only focused on the marine habitats. So you do some kind of pre-processing where you do some masking, some stretching and mosaicing. So you do some levels of pre-processing in order to be able to have accurate data set to be used, so that the outputs coming from your models are reflective of the actual situation, not to be confused with other features that you don't want to look at. Great questions. Thank you so much for these questions. And I think in terms of timing, Rashmi, you are doing really good.
Yeah, we're doing really good. Unless there's more questions,
Yeah.
We have a couple more minutes.
Sure.
So this is good.
Yeah. Yeah, I think I don't see any more questions. I don't think I skipped any of the questions. I think I went.
No, you got it all.
Yeah,
I've
yeah,
been
okay,
monitoring
great.
it.
Yeah.
All right. Well, in that case, thank you everyone for calling in, and happy holidays.
Thank you so much for having me.
Thank you.
Taylor, how are you?